Okay, now, it's probably on at least some of your minds, when do we actually have work for you to do? Don't worry, that's coming soon. There will be 15 assignments through a semester. So 15 that are reading questions and then 15 that are homework assignments. And it's all bundled together. So when I post the first set, which I'm aiming to do by Monday, that'll have the first batch of reading questions, first batch of homework problems. Homework problems are mostly taken from the textbook. Reading questions are my own nefarious creation. Now, one thing to keep in mind, it might seem kind of weird, is that the material you see in the reading questions would actually be slightly ahead of what you see in the homework problems. Because the homework problems are meant for, here's what I've already covered, now go do these problems on it. Reading questions are designed to encourage you to actually keep up with material. Maybe, God forbid, read ahead a little bit, since you know what I'm going to be covering. How many of you have already either printed out the notes or have them on your computer to follow along? Oh, that's not good. Okay. Keep in mind why I asked that. So it'll just make it a whole lot easier. Okay. I know that the notes are pretty voluminous. There's like 100 pages. But do you have a question?
What notes?
What?
Are they on the website?
Yeah. Yeah. That's why I encourage everybody to visit the website. And it's a good idea because there's all these links down the left. You look at each individual page. But I also pointed out on the resources page. Okay, so just. That's a lowercase l. And we have these sites set up for every class I've ever taught at USM. So if you just change the course number, you see a site for that course, in case you're want more resources than anything else you're taking. And then on the links on the left, resources, you'll see a PDF that has all the notes. And that's really what I'm going to follow. I honestly haven't even looked at the textbook yet. So, I looked at it years ago. It's one of those, kind of like a movie you see once and it's like, eh. So, and now, basically look at to see, okay, what homework problems do I want to give from it? There's the lectures page where you see the schedule. If a schedule should change for any reason, like if we have another tornado, which actually happened the last time I taught this class, then I'll update. If I need to change any due dates, I'll announce it in class, but I'll also update the site. So keep up with the site. And then there's even a page for my cats. You can check out cats. So everything the class website should have. Okay. Your questions? Okay. Let's see. Okay, nobody sneezed in this row. Top of the board all the way to. All right, here's my barrier. So first, I want to do a quick example from what I covered last time. So this is a kind of differential equation that I solved. So we have ay minus b, where a and b are constants. Later we'll see what to do when a and b are functions of time. I should mention, in the textbook, most of the time the independent variable is they use x. I prefer t just because in applications, most of the time when we're solving a differential equation like this, the independent variable really does refer to time. But they like x, I don't know why. So. But whatever independent variable we're dealing with, and it's at this level, it's important to not get too thrown off by um, changes in notation because mathematicians can never agree on notation. I had a colleague at Stanford who was teaching linear algebra and how to solve system linear equations, ax equals b, and then on a midterm put a problem, solve the system cx equals d, and got complaints like, you told us how to solve ax equals b, but not cx equals d. And if you don't know why that's ridiculous on their part, then you're too hung up on notation. Okay. Now, the solution that was derived last time turns out to be yt equals b over a plus y naught minus b over a times e to the a t minus t naught, where we have the initial condition y of t naught, your initial time, is equal to y naught. And I like to come up with solution formulas like these where you can see exactly how the initial condition is taken into account, and something that can save you, needs to save you time on the test if you learn to solve problems in this manner. So as an example, consider this equation, dv dt, where v refers to velocity. This is our following example, following object example from last time. 9.8 minus v over 5. Now, considering that v refers to velocity, what's a 9.8 for?
Gravity.
Gravity. What units?
Meters per second squared.
Yeah, meters per second squared. Okay, so that is your gravity constant for these units. Of course, as a mathematician, I'm obligated to really not give a bleep about units. So that's what students write on tests, like work out this integral, like if the integral refers to area or volume, and then they'll write in there, whatever the answer, numerical answer is, and then units squared or units cubed. It's like, okay, whatever. You sure told me. So if pattern matching is very important. It's one of the most important skills in mathematics you can have. If you want to fit this to this situation, what are our constants a and b? What is a?
It's 1.
Yeah, minus 1/5. Okay, and therefore b must be. Actually, it's not. Negative 9.8. Yeah. All right. So it's little sign mistakes that can often come up. So now what we can do is we can just, based on this, we can just write down the solution. Okay. So we're just going to have b over a. So the minuses will cancel. So we're going to have 9.8 divided by 5. Okay. And no.
No,
Divided by 1/5. Okay. All right. This is the reason why I have the notes. Almost all the time, I might mess up, but the notes are going to be right. It's very rare when it's the other way around. Because when you're up here in front of a class, your IQ gets cut in half. Okay. Especially at this hour. Okay, so b over a, 9.8 divided by 1/5, so times 5. Okay, plus, and then I should impose initial condition. Okay, yeah. Not y. V, because v is my dependent variable in this case. So, yeah, you look at the solution formula and see y of t equals like, oh, okay, that's my solution. Well, no, it's not. It's very easy to get hung up in using like generic letters for everything. F, X, Y, and so forth. But when you get to an application, you want to use letters that convey some meaning. Like when you learn to find inverse functions, it's customary, like you have y equals f of x, and now you're supposed to find y equals f inverse of x. And they tell you at some point to switch the x and the y. which is crazy because suppose your variables actually have some meaning, like m is mass and v is velocity. You're really going to switch those? But, okay, so the whole point is for you to not only learn from your mistakes, but also learn from mine. So my initial condition that I'll impose is v is 0 equals 50. So this is the initial velocity of a falling object. And from the example last time, we're using downward orientation. So downward is positive, so the object is falling at a rate of 50, and just this once, I'll put a unit, meters per second. So based on our solution formula, our initial value, 50, is what goes here, and then minus b over a again. And then we have e to the a, so a is minus 1/5. And then we're just going to have t in this case, because we have t minus t naught, but our initial time is 0. Okay. So now the problem is solved. All we'd have to do, if we really want to simplify, of course, we can. By the way, whoops, 9.8. Okay. Although I never actually multiply by 5. I actually multiply by 10 and divide by 2 because it's easier to work with those bases. So 98 times 10 divided by 2, 49, plus minus 150. So then we can finish simplifying from there if you really want to. So, all right. Now, the object is initially falling at 50 meters per second. So the fact that we have this exponential here, e to the minus 150, so what is happening to velocity over time? For instance, if I let t go to infinity, what's going to happen to this? Well, first of all, what's going to happen to the e to the minus 150?
T goes to infinity, approaches 0.
Yeah, so this part is going to go to 0 as t goes to infinity. So in the long run, what's the velocity of the object going to be?
49 meters per second.
Yeah, so wow, big change. Okay, that's one thing we'll be looking at is what's the behavior of a solution over time, especially as t goes to infinity. What is the long time behavior? Okay, so any questions about this one? All right. I know I complain about the erasers, but it doesn't mean it needs to run away. By the way, most of you, well, I'm sure any of you one time or another have class across the hall in 303, and I believe it's still there, like on to the side of the board, there's a whole bunch of black markings and so forth. I did that. No, because there, instead of erasers, they have like rags to wipe the board, and I pick one up to erase the board, and it's got ink and crap all over it, and so I can't erase the board. So I thought I'd wipe it on the board, and the department chair at the time wanted to know what, in his words, animal did that. And poor Lisa in the math office still complains about it to this day. It's like, sorry, it was 5 years ago, get over it. Okay, now, one thing that we will look at from time to time is called a direction field for a differential equation. So the first part of the course will be devoted to general first-order differential equations of this form. And I say first order because the only derivative involved is the first derivative of y with respect to t. F describes the time derivative. So f, and I'll probably never use this term again all semester long, but just for completeness I'll put it in. It's a rate function because it's describing a rate of change of y with respect to time. In order to draw a direction field, for this kind of differential equation, it's a bit really repetitive, very tedious process. So you choose points in the ty plane. So t-axis, y-axis. Okay. So for each of what ought to be preferably a zillion points in the plane, or you can just use software like I did for direction fields in the notes, what you do is you evaluate your rate function at each such point. And keep in mind that that gives you y prime at this particular point. This is a notation you may have seen in other classes. You'll certainly see it more in this one, where I do a vertical bar, and that indicates that I'm evaluating this expression at whatever point I indicate down here. Okay, so we know that's a derivative, but what does a derivative mean, as you should know from Calculus 1?
Slope.
Yes, it's a slope. So what you do is, on your direction field, at the point t naught, y naught, you draw a vector. So t naught, y naught is like the initial point, and then make sure that the vector has the slope that you just computed, that value of f. Now, as far as how long you should make the vector, preferably not long. Like, for instance, if you are choosing points on a grid, so this is one of my points, t naught, y naught. I plug this point right here into f and say this is the slope that I get. Then preferably, because I'm going to have more points up here surrounding this point, you should make sure that it fits within one grid cell for whatever direction it's going in. You don't want to have these vectors, since you could be drawing many of them, you don't want to have them overlapping. So once you have chosen enough points and drawn enough vectors, then you can get an idea of how your solution behaves. Okay. Actually, how many of you have ever used MATLAB? Okay, yeah, and use it all the time. So MATLAB has a very helpful function called quiver. That's very clever on their part to draw a bunch of arrows. So if you have a collection of all these points, like your t values and your y values, and then you compute all these vectors and you pass them as additional arguments, the quiver command will plot a direction field for you exactly like this. And its default behavior is to make the vectors short enough so that they don't overlap one another. Okay, so in the notes, I have a direction field for the example I just did. So I'll erase this particular vector. And so at the So here's the initial value that I've chosen for the example, is 50. But I want to highlight 49 also, because this is for y prime is equal to 9.8 minus v over 5, which if I were to factor out a 1/5, then that would be the same as 49 minus v. And it's helpful to write it in this form because what we can see is that y prime is 0. Sorry, but I keep messing up and using y instead of v. All right, so for this example, this would actually be the v-axis. So this is your dependent variable. This is our independent variable, which will almost always be t. So the derivative is 0 if v is equal to 49. Well, when a derivative is 0, then how is v prime is equal to 0? How's v going to behave?
It's going to remain constant.
What?
Is it going to remain constant?
Yeah, it's going to be remain constant. So if the initial condition is 49, that means that v of t is going to be 49 for all t. It'll remain at that value forevermore. So I'm going to mark this here. And when that happens, so we have v prime is equal to 0, we call that an equilibrium solution. So it's important to know for a given differential equation if you have any equilibrium solutions, and if so, what they are. Okay. So then it's interesting to see if your initial value is not an equilibrium solution, then how's it going to behave? And what you would find, now we saw from the example, we started off at 50, that you have this exponential, this decaying exponential, this decaying to 0, and so what happens is the solution, and this is what your direction field would show, is converging to 49. If you had chosen an initial value below 49, well, say something smaller, and yes, I know my scale is really off, deal with it. Let's say it's 47. Then, again, the solution is going to tend towards that equilibrium solution. It's going to take a while to get there, but eventually it will. And in fact, even if we choose initial values that are much further away from 49, we're still going to see this behavior. So that equilibrium solution of 49 tends to attract solutions that have different initial values. And so I'll just hold this up to the camera. So this is a direction field, which you can also see in the notes, that no matter what the initial value is, it's going to tend towards 49. So we'll discuss this more in the later section, where we say that this equilibrium solution is stable, that it's attracting solutions of different initial values. We can also see unstable, where the solutions for different initial values will trend away from it. Sometimes it can trend toward it on one side and away from it on the other side. That's called semi-stable. So these direction fields are a good way to visualize how solutions of a differential equation are behaving for many different initial values. Is there a question? Okay. Well, as you can tell from this example, I try to avoid drawing direction fields by hand, especially when I know I have software to do that. And no, I'm not going to make you draw one on a test. That's just cruel. Not only because it's really tedious, but I know you guys are generally not good at graphing. Like sometimes it's so bad that I start to lose my own graphing ability. Yeah, it's like a curse or something. Okay, now So a better way to wrap up class, on a Friday than to dump a bunch of terminology on you. If we're going to be seeing several types of differential equations throughout the semester, now there'll be far more kinds that we don't deal with in this course, but in other courses. There are at least 2 courses that directly follow this one. There's 415 that's offered every fall, and that's focused mostly on ordinary differential equations still, but with applications to mathematical physics. And then 417 that's offered only in the spring. That's on partial differential equations. So if you've taken Calculus 4 already, or you are now, then you see partial derivatives. So that class plus this class gives you partial differential equations. Do we have any physics majors in here? Okay, yeah, so if you haven't already, you have to take both of those classes. But no one else has to take them, and I think even many math majors choose not to, but I highly recommend them because they're one of the most important applications that we see. It's good for employability anyway. Also, numerical methods for partial differential equations is my research specialty. So it's important to be able to classify differential equations. There are many different properties they can have. Because once you classify it, then you're going to have, by the end of the semester, a basket of solution methods to dip into, and what kind of equation it is affects which solution method you're going to use. Okay, so in this class, we are concerned only with ODEs, ordinary differential equations, and versus PDE, which is a partial differential equation. And the way you distinguish between them, it just depends on whether you only have one independent variable. In that case, then it's an ODE. So generally that is going to be t or x. So your solution is a function of only one variable. Now, your solution may be a vector valued function. So you can have like a system of differential equations. We'll see that a time or two. So you can have as many dependent variables as you want, but you only have one independent variable. Partial differential equation is more than one. Bless you. Told you not to sneeze. That's okay. It's actually not my laptop, it's the department's, so. Okay. I was a Windows person until a year and a half ago. And your multiple independent variables can be x, y, z, t. That's what it is in most applications. Okay. Okay, but so now that I told you that, you can just forget about PDEs. Unless you want to take 417 next spring. I think Dr. Zhu normally teaches that class. I did it once. Okay. Actually, one of my favorite examples of a PDE is like a partial of u with respect to t is equal to some constant. And I write k squared to convey that the constant is positive. And then we have a second partial of u with respect to x. This is called the heat equation, which I derived at the end of 280 last semester. Some of you might remember that. Where u refers to temperature and shows how the temperature changes within body of however many dimensions. Here I've written it for one space dimension, but you can have multiple space dimensions and adjust the equation accordingly. The constant k needs to be positives because what happens to temperature over time if there's no heat sources, it's just going to diffuse to an ambient temperature. Whereas if this was negative, you'd have diffusion happening backward in time, which leads to exponential growth rather than decay, which is a little bit non-physical and kind of weird. Although I actually work with equations like this, where the constant can be positive in some places and negative in others, because that could be used to enhance images. Diffusion is used to smooth out images, to remove noise or fuzziness. Negative constant is used to sharpen images. Okay, so that's my shameless plug for my research. Now, that's one property. Is it an ODE or a PDE? Now next, I used this term before. The order, this applies to any differential equation, ordinary or partial. That is the order, so that is the highest order of a derivative that appears in the equation. Okay. Now, so y prime is some function of t and y. That's what we're dealing with in the first part of the course. That is a first order ODE because we only have a first derivative. But later, like the next chapter after that, chapter 3, we'll do equations of this, like this one. So this is second order because of the second derivative. When we get to chapter 4, we'll cover higher order equations than that. One of the most interesting applications are equations that are second order, whether they're ODEs or PDEs. Although one exception is actually a PDE. Partial derivative with respect to time is the fourth partial derivative with respect to x. This is called the beam equation. Where u is the displacement of a beam. Because the very common equation is where we have a second derivative. That's for like a vibrating string. So u is again modeling displacement. But you definitely would not want a beam to be displacing in the same way as a vibrating string. So we definitely want these displacements to be very small. Okay. Now there are other ways to distinguish, and even among equations of the same order, distinguish equations from one another. And we'll see equations of several such types. Okay. So linear versus nonlinear. Okay. Now, so the easiest way to describe linear versus nonlinear, so DE is linear if any coefficients that it has do not depend on the differential equation's dependent variables at all. And I'll give some examples of linear and nonlinear so you can tell the difference. Most of the time, well, in the first chapter, chapter 2, we'll be solving equations. We'll see both linear and nonlinear. After that point, it'll just be linear, because nonlinear, real pain to solve. So in fact, equations, all the, actually I'm going to be lazy here. All the examples, I should say all the specific examples. Number 2, everything on the previous board. That heat equation, that beam equation, that second order equation, all of those are linear equations. In fact, for those particular examples, the coefficients are constant. Most of the time we're dealing with constant coefficient equations, again, because they're easier to solve. Well, like, I actually deal with variable coefficient equations in my research. So the example of that is, so more examples of linear equations. So something like y prime is equal to 2t y plus e to the t. So we can have nonlinear functions of t, we just don't have any nonlinear functions of y, or y prime. So because of the 2t here, we say this is a variable coefficient equation because the coefficient is no longer a constant. But still linear equation. This equation, before too long, you'll see how to solve it. I think we'll probably get to that next week. Okay. So for instance, even an equation like this, du dt is equal to partial with respect to x of a coefficient alpha x squared that depends on x. So this is also linear. And even in the case where a coefficient is, say it's I'm solving this equation for x between 0 and 1. So I define this coefficient to be equal to 1 when x is between 0 and 1/2. And then for 2 otherwise. So here we have a discontinuity in the coefficient, but it's still a linear partial differential equation. I've actually had 2 honor students in a row work on various problems of this kind, or various situations. This kind of equation comes up where your medium, your spatial domain, consists of different materials. This alpha reflects thermal conductivity. If you have heat energy passing through one material and then shifting to another material, the conductivity is going to be different, so that changes your coefficient. But if but each one of them is homogeneous, but you still have a change at some interface. So these kind of interface problems are very important in applications. Okay, that's shameless research plug number 2. Okay. Example of a nonlinear equation. It happens to be a PDE. It's called the Burger's equation. These kind of equations come from modeling conservation laws. Here, the coefficient is the same as the dependent variable. It's u, so that's what makes it nonlinear. So these could be modeling fluid flow, also modeling traffic flow. Have you ever had a situation, and maybe you don't have as much in Mississippi, because it's not like we're used to living in California where you have 8-lane freeways all over the place, but you're driving along at pretty good speed, all of a sudden you've slowed down for no particular reason that you can identify. There's no construction, there's no accident, all of a sudden things just slow down for a bit, and then you move again. That can actually be explained mathematically from these kind of equations. Want to know more? Take 417. Okay. Let's see, an example of, I'll change this example to make it nonlinear. Y prime is equal to 2y squared plus e to the t. That also is that's a nonlinear first order ODE. So the y squared there complicates matters a bit. Okay. Now, and then some nonlinear equations we just would not be able to solve. We might actually linearize them to get an approximate equation that we can solve. Okay. So those are various ways of distinguishing equations from one another. And we'll spend a lot of time on these linear variable coefficient, or mostly linear constant coefficient problems, like this one right here, this second order one. Okay. Now, the last comment I want to make is about how you define a valid problem involving a differential equation. At least to the concept of what is called a, I'm sorry for anybody watching that I keep forgetting to move the computer. Okay. Start packing up. We're running from here in 4 minutes. a very important concept of a well-posed problem. So in order to have what's called a well-posed problem, first of all, the problem must have a solution. Second, the solution is unique. And finally, solution depends continuously on the problem data. Data is a broad term. It could refer to the coefficients of a problem. It could refer to initial data. Any of those things constitute problem data. And so the first two are kind of self-explanatory. But if I just give you a differential equation by itself, yes, it'll have a solution generally. May not have a unique solution. You need often to specify certain conditions to go with a differential equation. Like in the example at the beginning, we needed initial condition. So you need initial conditions, or some problems have what are called boundary conditions. In this class, we'll deal with initial conditions. For instance, if we have a differential equation of order n, we need to have n initial conditions to go with it, and that will ensure a unique solution. Sometimes, though, a differential equation could still fail to have a unique solution. Maybe more than one solution is possible. These are rather strange situations, but they do happen. Okay, and certain like graduate classes we see that. This one is a little stranger. Another way I like to explain this is if you have a small change in the problem data, just take initial condition. It's like the falling object example. If I tweak the initial velocity just a little bit, that should not lead to a large change in the solution. This is why, for instance, solving an equation for heat diffusion going backward in time is not a well-posed problem, because there's exponential growth involved. You tweak that initial data at all, it will eventually cause arbitrarily large change in your solution. This is important for like numerical computation. A lot of equations can only be solved approximately. If you know that your problem could have a situation where the initial data, which might be based on measurements, is thrown up by a tiny bit, and your solution is thrown up to a large degree as a result, then how can you trust your solution? So it's very important to make sure your problem is well posed before you try to solve it, either on paper or approximately. Okay. All right. So you've suffered enough. We'll start actually solving equations on Monday.